Now, I'd like you to imagine that inside this circle here, sort of rough circle I've drawn, this is basically the universe. And inside the universe, because we have the kind of cosmological principle, it's isotropic, it's homogeneous, we have this kind of distribution of galaxies around here. Now, what I'd like to do is I'd like to imagine that we have a galaxy that's at this point over here. And if I just kind of put a ring to sort of show where that is, maybe this, obviously everything at some point existed at zero space down here. So this is where the Big Bang happened. And then the universe has got bigger and bigger and bigger. What's it expanding into? Well, nothing, it's just making the space. And what we can think about is perhaps this galaxy has a mass of m. It's moving out at a velocity of little v. I've made that a little to make that kind of sort of clear. And it's at a distance of r from the centre of effectively where the Big Bang is. And yeah, there we go. So basically we've got a galaxy of mass m moving at velocity v, and it's travelled a distance r since the beginning of time. Now, what we can think about is the energy it needs to basically keep on escaping and not kind of sort of collapse back in this. Basically, if it's not moving fast enough, it's going to sort of basically get to a point and then kind of everything's going to collapse. So what we can think about is the potential energy is equal to gmm over r, where here m is basically the mass of everything inside this inner sphere that's kind of sort of pulling it back in. So the galaxy has mass little m, and there's a certain mass of stars kind of between it and like where it kind of started, which is kind of pulling it all in. So what do we know? Well, the mass of all of the galaxies within this area here is equal to the volume multiplied by the density of the universe. And again, if it's isotropic and homogeneous, we're going to talk about effectively the average density of the universe here. But the volume of this thing here, because we've got 3 dimensions, is equal to 4/3 pi r cubed. So what we can do is we can put this v into this equation, and then we can replace the m term with this equation down here. So what we can say then is that EP is equal to g times 4/3 pi r cubed rho m divided by r. So I'll just give you a bit of time just to have a look at that. We've replaced v with 4/3 pi r cubed. We've multiplied it by the density, and we've replaced the m term up here. So what do we do next? Well, if we think about this thing which is escaping, in order for it to escape, we need to maybe know its kinetic energy. So Ek is equal to 1/2 times the mass of the galaxy times its velocity squared. The velocity is equal to Hubble's constant times the radius. So effectively, if we know it's travelled this distance in a certain amount of time, we know that its velocity is equal to h naught r, and I've got another bit of another video that kind of explains that in a bit more detail. So we can then say, well, v squared is equal to h naught squared r squared, and I can then replace this v squared term here with h naught squared r squared. So we can say that the kinetic energy Ek is equal to 1/2 times m times Hubble's constant squared times the distance squared. So I now have my equation for the potential energy and my equation for the kinetic energy. Now, in order for the galaxy to kind of keep moving away rather than sort of collapsing in due to kind of the fact that everything's got mass and it's kind of sort of pulling inwards, it needs to have a certain velocity. And basically we can think about the limiting factor when the kinetic energy is equal to the potential energy, and this will be at a certain critical density of the universe. So what I can do then is equate these two things here, and I can replace the density of the universe with what we call the critical density, and it'll hopefully become clear in a minute. So what I have here is my potential energy. I've got r cubed over r, so I've just taken the r out, and that's equal to 1/2 times m h naught squared r squared. So what we can now do is maybe tidy it up. We can see we've got the mass of the galaxy on both sides, so that can be cancelled, and we have an r squared term as well. So I can then say that g times 4 pi rho, and this is going to be the critical density that we're talking about here, over 3 is equal to h naught squared over 2. Now what I can then do is make the critical density the subject, and I can say the critical density is equal to, well, I'm going to multiply this by 3, h naught squared, over, well, I've got divided by 2 divided by 4, so that's divided by 8 times pi times g. And this here is the equation for the critical density of the universe. Now, you don't have to know the derivation, but it's useful to see that these numbers haven't just sort of been plucked out of nowhere. And they're based on many assumptions. The fact that we have, like a uniform expansion of the universe. We need to know things like Hubble's constant, which has loads of different uncertainties in actually measuring that. And if we know that, we can actually work out what we call the critical density of the universe. And this is the point at which the universe won't basically collapse in on itself.